play this movie again. It's sort of fun to look at. But basically, we've got little black holes that are forming inside of the nucleus as these droplets exclude chromatin. And so what's been something that we're really interested in is what does that mean mechanically when you have coupling between phase separation and the mechanics of the genome? After all, we think of our DNA as software, but it's also hardware, right? It's a physical object with a persistence length and so forth. So it's a kind of entangled polymer network that has some viscoelasticity. And the elastic component of that network can actually contribute to the overall energetic calculation for thinking about whether these droplets will form, where they'll form, and so forth. We were inspired, I want to just highlight, we were inspired by this beautiful paper in a non-biological system by Eric Dufresne's group, and started to look for these effects in our system, and I'll show you that that's what we think is happening. There's a mechanical effect. And the reason for that is, I should go back and just show you, the idea here is that if these droplets are trying to nucleate time compared to the softer regions of the genome. And it's known that there's a lot of heterogeneity in the mechanics and the compaction state of the genome. So this is a case where we try to nucleate droplets within a dense, what's referred to as heterochromatic region of the genome, a transcriptionally silent region of the genome. And when we do that, so I'll try to put a droplet in this dense region of the genome. What you see is that these red droplets do not go inside that heterochromatin region. Instead, they decorate the outside of it like flower petals. And we think that that's a mechanical exclusion effect. We can actually simulate that together with our collaborators, Joel Berry and Miko Mataya. We can simulate that mechanical effect because we think it reflects this mechanical energy deprivation contribution to the phase behavior. So I'm just about out of time here, so I just want to make a couple last points. One is that these droplets can still pull genomic elements together through coalescence, and we can see that here, and we think we're able to use that to actually measure some of this mechanical stiffness of the genome. What that means, though, is that the droplets, if they're attached to particular genes, they can pull them together through coalescence and actually activate genes that way. But non-specifically interacting parts of the genome are excluded through this exclusion effect that I showed. So we think this is a kind of way in which phase separation is rearranging the genome in a kind of smart way, filtering out the non-targeted regions of the genome and bringing together the target regions. So I'll try to tie this up here now. At the beginning of the talk, I told you that a key kind of poorly understood part or length scale of biological organization is this mesoscale level. We think that liquid-liquid phase separation is a key aspect of organization on that scale. We think many of these organelles, really dozens of different types of organelles in the cell, are assembling by liquid-liquid phase separation. There's a lot to figure out, and there's many ways in which we think there's going to be new physics at play that go far beyond the sort of equilibrium statistical mechanics pictures that we're using now, because that's kind of what we have. And I think that the multi-component non-equilibrium features, it's a whole playground for condensed matter physics, and I hope you'll join me in this adventure. So I think I mentioned key individuals as I went through the talk, so I won't list them again here, but I just want to thank our group. We have a really fantastic interactive group, and I'd like to thank the people who funded us over the years, and thank you again for your attention.
Wonderful. We have some time for talks. Yes, please, over on the right.
Professor Brangwyn, thank you very much for certainly one of the most beautiful talks I've seen this week. Congratulations on some amazing discoveries. I had a couple of questions on some of the details of the phase separation. So you showed some pictures of spinodal and monodal decomposition, and then the more classic balancing the surface energy versus the bulk energy to drive the phase separation. And so in that movie that you had of the droplets that were trapped in the actin network, that essentially prevents the droplets from coalescing and growing that way. But you would also expect if this were an equilibrium process that you might see the analog of some Ostwald ripening, where smaller droplets disappearing at the expense of the bigger ones, and the actin network would prevent the coalescence, but you should still imagine some distribution maybe from smaller droplets disappearing. So is that a sensible way to look at it? And I didn't see, at least in the movies I saw, do you see small droplets disappearing while the larger ones grow in cases where coalescence is blocked?
Yeah, this is a good question. So Ostwald ripening effects, we think are playing a role, and so we explored some of that with the nucleolus in the experimental system of the C. elegans embryo. In the frog oocyte system, you don't usually see shrinking of those droplets, the small ones at the expense of the large ones. I mean, the Ostwald ripening effect, as you know, is ultimately mediated by surface tension, and these surface tensions, as for other macromolecular liquids, tend to be small. So you sort of order of magnitude say the surface tension would be kT over some molecular length scale squared, and these are macromolecules, so the surface tensions tend to be low. And so we think that Ostwald ripening is less important here than maybe in some other systems.
You wouldn't expect proteins to diffuse through these distances between droplets, of course, in that way.
Yeah, I guess what I'm saying is there are places where we think Ostwald ripening is at play, but in that frog oocyte system, we don't usually see that. And I think most of the droplets themselves are already quite large, and the surface tensions are small, so we think it's less. That's why it's not visible there.
Let me take a question from the left-hand side.
Hey, Cliff, it's Sarah.
Hey, Sarah.
I want to learn a little bit more about the nucleolus. Is it always the case that you have NPM1 and tuberculin phase separating within the nucleolus, or is that only under particular conditions?
Yeah, so that's generally that's what you find in the textbooks, and that's what we see in these systems. I mean, they are in separate compartments. I mean, there's some partition coefficient, right? So you can have some NPM1 within the FC, within the triple iron rich, and vice versa. And we actually are actively studying, the partitioning and sort of the physics of partitioning, if you like. But yeah, that's not induced. There is a way to induce a sort of a higher order demixing if you turn off RNA transcription, which I can tell you about offline. But that's the native state.
Okay, cool.
Yeah, good.
I think I'll request further questions, hopefully right after this.
Sure.
I would like to thank the speaker and all the speakers.
Right.
Yeah, I'm also very honored to be chosen as a speaker for the Kavli Symposium. I want to really thank the Kavli Foundation and the committee who selected me for the speech. And I have to thank especially the chair for giving me this complex title. So the title was not my choice. So the title came from the chair. And first I thought, is it student? I would send him home, okay? But anyway, I thought, no, it's a really fantastic title because it says more or less everything what I want to talk about. So I want to explain you maybe don't know Heusler compound. I want to explain you. Then I want to explain you how I can use the periodic table as a Lego box to build maybe most of the states you are interested in. So I'm at the beginning of the symposium, so I'm talking about the unit cell. So I have an easy game because the unit cell is quite simple compared to the complexity of biological cell, but I think it's easy then also to go with the next talk because I use some of the features like topology to explain the properties of my material. So I'm talking about a family of compounds, Heusler compounds, which have a simple cubic unit cell. If you see there, all the three lattice constants are the same, and you have a few atoms there. It looks quite simple. The other thing which I want to say, 2019 is an important year because we have two celebrations, and one is a celebration of 150 years of the periodic table, and because Mendeleev wrote the periodic table down. You see here an example of the periodic table, but there are other possibilities, and as you see also LEGO, this is an official periodic table which I found in the internet, LEGO periodic table. The second celebration we have in 2019 is 125 years of Heusler alloys. This compound were invented by Fritz Heusler, you see here a photo, and he was an owner of the copper mine, and the company which made alloys was copper and manganese to make thermocouples. In his free time, he mixed some additional elements into the compound, and manganese, copper, and aluminium, we know, are non-magnetic, and he mixed the three elements together, and he was surprised because the result was a ferromagnet at room temperature. So this is a surprise for itself, and we have a few toys, only 3 toys here in the room if somebody wants to see. So you will see copper, manganese, and aluminium are non-magnetic in your plastic box, but the Heusler alloy is a ferromagnet at room temperature. So the compounds very often have nothing to do with the elements they made from. So then I come to the next part. So as you remember, now you understand what is a Heusler compound. It's a simple cubic compound. So we have the Lego box, and our elements of the periodic table, they have a certain color, and the color is related to the atoms. You see, we have here green, blue, and red boards for the Heusler compound, and all the elements which are available for the green position are here in green, all the elements for the red position in red and the blue. And now the mathematician in the room can calculate how many possibilities we have to make new compounds. So I can retire on Heusler compounds. Okay, and this is the way we do it. Here you see me and Pescher, my old assistant, trying to make new Heusler compounds. So we have our periodic table, and you see there are some elements around in the periodic table, similar like the toy box maybe you have here in the room now. And then we choose which element we combine and what we try new. So there are two different classes of Heusler compounds. One are the so-called half Heusler compounds with the composition 1, 1, 1, X, Y, Z. So they are 3 interpenetrating SVC lattice, and then there are the
So anyway, what is very exciting, of course, are the applications. Okay, it's one thing to produce very high intensities, but the applications which follows are really mind-boggling. So I'm going to start. Does it work? Oh, okay. Well, no, went too fast. Went too fast. Yeah. So, like Donna said, everything started, with this man, Ted Naiman, okay? May 16, 1960 was the first shot, laser shot. Anyway, and, there's one thing which is really mind-boggling about lasers is the fact that, you can use light, to slow down atoms, and you can slow down atoms to very, very, small kinetic energy, micro electron volt, nano electron volt, these kind of things. And that, of course, led to the development of this beautiful field of quantum optics and cold atoms and so on. But also what you can do, and when this is really, you can do just the opposite. Instead of slowing down atoms, you can accelerate, particles. And you can accelerate particles to very, very close to C, very, very large Lorentz factors. And that is really remarkable. And now we can really accelerate particles to the GeV with no doubt, and one day we are going to go to the TeV. So you can see that with one EV atoms, photons, from the lasers, you can really go through about 20 orders of magnitude from the nano EV to the TeV. Okay, this is remarkable, and that, of course, always fascinated me. And there is a lot, as you will see, there's a lot of room, about. So this is, of course, Chern amplification. I'm not going to describe it. Donna didn't take very well. But what we can do now, we can produce power, peak power, of course, peak power, which is expressed in petawatt. Petawatt is 1,000 times, okay, the global grid power, okay. So it's phenomenal, but of course we do that only in few femtoseconds and not, CW. So we're cheating a little bit. But now, what is important also, if you can focus this power over the wavelength of light, you can produce enormous intensities, which is associated to enormous pressures. And the pressures, attend to the 23 watt per square centimeters, is of the order of 10 million times the Eiffel Tower on the top of your fingers. So this is really significant, of course. So, but there is more than this, because producing this extreme light, that's what we call extreme light, it can also produce this largest temperature, this largest pressure, this largest acceleration, this largest field, and the laser becomes, in fact, a universal source of high energy particles and radiations. And so this is exactly what we show here. If you are focusing this petawatt laser over small spot size, then you are getting, electrons, not at the TeV yet, but it will come, protons, gamma rays, high field, all kinds of radiations and particles, could be created. So this is extremely exciting, and what is exciting is the fact that, lasers, until CPA, I would say, was basically dealing only with atomic physics, EV physics, okay? And now, of course, with this possibility to increase the peak power to get enormous value, you can go to the subatomic regime, and that is very exciting, okay? So you can really go now in GeV and TeV and so on. Now this is, here I'm describing, where's my pointer? Okay, yeah, it's working. Okay, so now the focus intensities that we can really produce as a function of years, is, if I'm looking at this ordinate here, at the beginning, when the Naiman came out, when we were at 10 to the 8 watt per square centimeters, and then some techniques like one-dotting and switching were developed, and we could go, and, we basically go up 10 to the 14, and that was really the plateau. And the reason why we were reaching the plateau is because we were breaking down, of course, the materials number, and Chern force amplification came about, and boom, immediately, the intensity took off, okay? And now we are at incredible intensities in a regime of 10 to the 23, 10 to the 24, and soon we will have the 10 to the 25 and maybe higher. And of course, as we are doing that, we are going into new different regimes in physics. The first one is not terribly exciting, but very, very important, for applications. It is the fact that we can use these lasers, to micro-machine with high precision, and because machining with femtosecond laser, of course, the heat doesn't have the time to take off. So you remove only, a very, very precise amount of materials without basically any collateral damage. So this is good. And this is what's nice also, you can use that on a piece of metal, but you can do that also on the eye, okay? And this is the CPA, in fact, revolutionized ophthalmology, because every year, I think you have 1 or 2 million patients, or eyes, which are having these procedures. So it's very, very, it's been very important for society. And so you can see that the lasers, can be focused, say, in the cornea here, and we can really take some very, very thin slip of materials, a slide of materials here, and you can, this way, you can correct the visions, myopia, hyperopia, astigmatisms, and so on. I'm not going to go very much here. For example, if you are really doing this thing with 50 picosecond pulses, 50 picosecond after all, it's kind of short, But this is, you don't get into the cornea something very clean. If you are using 300 femtoseconds, very, 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 very clean. Anyway, so I'm not going to. Now we are going to go into more physicsy things. So as I said, after 1985, the intensity took off, and we were crossing new regime. And the first regime, of course, what we crossed was this relativistic regime. The regime where really the electrons around the nucleus now could reach the speed of light, change its mass, and so on. So and the optics, of course, regime completely changed, okay, because of that. And one of the very important applications you will see is going to be in producing very high energy particles, in electrons first, and then in protons. So electrons, in order to produce particles, to accelerate particles with the laser, what we do is something which was introduced by Toshida Tajima and Dawson in 1979. But of course, they had to wait for the laser, for the CPA to be able to use it. And this is a technique. Yeah. So the technique, in fact, is very simple. Okay, you take your laser source and you whack it into this plasma, supersonic gas jet, and you are going to ionize the plasma. And you are also going to generate a plasma wave, very strong plasma wave, which is going to basically propagate at the speed of light. And the electrons, are going to go when you do surf, the electrons are going to be trapped, or some of the electrons are going to be trapped into the trough or into the plasma wave and be dragged at the speed of light. And what is absolutely amazing is the fact that because it's a plasma, you don't have to worry about damage threshold. This is the thing which is limiting conventional acceleration techniques. You can really put a lot of, you can have very large intensity to deal with, and so you can produce very high energy beams. And typically, the energy beams that you can produce is in GeV per centimeters. Okay, for the people who don't really know what a GeV is, well, if you want to produce if you want to produce GeV beams, okay, you need this kind of facilities. Here, for example, at Synchrotron Soleil, 3 GeV, enormous facility. And you see that what we do is we can produce that over centimeters. Now, it's typically GeV. We are at 4 GeV, but it's only the 4 GeV can hold in my palm, in my hand. So now, if I'm looking at, for instance, LHC, there's a lot of people high in physics, I guess. So this is a TeV machines, and because they are using, of course, a conventional technology. It's 27 kilometers, okay, because you can only produce MeV per centimeters. But if you were using, that's microwave, we are using microwave cavity. Now, if you are using, of course, laser wave field acceleration, in practice, the system will really be of the order of a few hundred meters in length. So enormous improvement. And so now, but you can do even better. We know that we could do even much better, in fact. And we could do very much better if we were, and this is what we are trying to do now, instead of using visible short pulse laser, you see you have a pulse which is about 20 femtosecond here, and you have about, the period is about 2.5 femtosecond. So you have something like 10 to 20 cycle in your pulse. Okay, now, what we are trying to do, I'm not going to describe it, I don't have the time, but what we want to do is really to produce single attosecond pulse, okay? And with efficiency, here we have several joules, and we'd like to have also a joule, or fraction of a joule maybe, at this. Because this pulse is attosecond, it's per definition, just Fourier will tell you this, is that you are in the X-ray regime. And so now, the idea is, that we're pursuing with Toshida Tajima now, is to go into this X-ray regime and try to do wake field acceleration because you are in the X-ray regime. Now you can do it in solid. And with solid, you have, of course, you are 10 to the 23, 10 to 24 electron per cubic centimeters, 6 order of magnitude above what we were using when we were using gas. So you should be able really to produce TeV per centimeters. Okay, this is phenomenal, and to think that you could have something like CERN, on a finger. Okay, it's a little bit provocative, but it's coming. Okay. Now we talked about electrons. We have to talk also about maybe protons. Proton also, we can do that very well. Okay, and in fact, we should be able to produce GeV for protons relatively easily and simple. Okay, here you have, for instance, a very thin target, nanometers in thickness, and you whack again the lasers, high intensity lasers into this target, and then you can get really proton accelerations. And now we have the records about something like 100 MeVs, 150 MeVs, but by using a technology I just showed you, which in fact is really relying on single cycle generation, I can show you, we should really be, we should produce this GeV very easily and very efficiently. And of course, this is the competitions. Of course, it's here. You have what is a GeV proton acceleration or something like that. So you see the immense simplifications, compactifications that we are getting with the laser. And of course, this is what gets us excited. So let's see, next one. Yeah. So of course, let's talk about application now. Of course, the fact that we can produce now, particles in the MeV GeV regime very easily. And in particular, we could really do something like proton therapy. Proton therapy is really the therapy of choice. Okay, because we